Welcome to the Explainer. Today, we're diving into a really cool idea. What if you could make AI algorithms way faster? Not by building a better computer, but by teaching them smarter physics. Well, a new paper by Tang Dang and his colleagues shows us exactly how that might work.
So, one of the biggest challenges for AI isn't just about getting an answer right. It's about the AI knowing how confident it should be. The real goal is for a model to understand the entire range of possible answers, not just to spit out a single one and call it a day. And that's where this technique called Bayesian inference comes into play. Think of it like this. Instead of just giving you one destination on a map, it gives you the entire map, showing you all the possible places you could go and how likely you are to end up at each one. This kind of possibility landscape is absolutely critical in high-stakes fields like drug discovery or financial modeling, where knowing the full range of outcomes is everything. Okay, but here's the catch. Actually exploring these complex probability landscapes is, well, computationally very, very slow, especially when they have thousands or even millions of dimensions. It's a huge bottleneck for a lot of modern AI. All right, so let's dive into this. To really get a feel for how these things work, we're going to use a simple analogy. We're going to look at how the classic algorithm, known as Langevin Monte Carlo, tries to solve this exact problem. So imagine our super complex problem is a landscape, full of hills and deep valleys. The deepest parts of those valleys? Those represent the best, most probable solutions that we're looking for. The algorithm, then, is basically like a ball that we let loose on this landscape, and its job is to roll downhill and find those sweet spots. Now, the ball's movement is really governed by two key forces. On the left, you've got the gradient. Just think of this as gravity. It uses the slope of the hill to pull the ball downwards, always towards better solutions. But that's not enough, right? Because it might get stuck. So on the right, you've got Brownian motion. These are like random little kicks that jiggle the ball around, helping it to pop out of small valleys so it can explore the entire landscape. This simple roll and kick method, it works, but it gets incredibly inefficient when the landscape is massive. And we're not talking about a simple 3D hill here. Modern AI problems live in these abstract spaces with thousands of dimensions, and this simple little ball just takes forever to explore them all. So, to speed things up, researchers realized they needed to give the ball an upgrade. They had to teach it smarter physics. Move it beyond a simple roll and jiggle to something a lot more sophisticated. And this led to a kind of evolution. The original algorithm, that's first order. Then came second order, which added momentum. Now the ball doesn't just roll, it builds up speed, it can cruise over small bumps, and it remembers which direction it was heading. And after that, third order LMC added even more complex dynamics to make it explore even faster. So the whole point of adding better physics is to improve what's called the mixing time. And that's just a fancy term for how quickly the algorithm can explore the entire landscape and really zero in on the true distribution of answers. A faster mixing time means a much more efficient algorithm. Simple as that. And this brings us right to the heart of the paper we're looking at today. Because instead of just building a fourth order or a fifth order algorithm, these researchers created a general recipe for any order P. A universal formula for speed. This table really shows the main result brilliantly. Just follow the rows down. That mixing time column shows how much the algorithm's speed depends on the problem's dimension, which we call d. For second order, it depends on d to the power of 1/2. For third, it's 1/4. But look at the jump this new work makes. The fourth order algorithm drops that dependency all the way down to d to the power of 1/7. That is a massive leap in efficiency. And they even give us the general formula for any order P you can dream up. And in their own words, by creating this general formula, they actually provided a positive answer to a long-standing conjecture in the field. They proved that yes, you can keep making these algorithms faster and less bothered by the problem size just by teaching them more complex physics. Okay, so the theory is super impressive, right? But does it actually work in practice? Let's take a look at how this new approach held up in a real-world experiment. So what they did was set up a classic machine learning task, predicting air quality levels using a real data set. The problem had 16 dimensions, and they put their new fourth-order algorithm head-to-head against the previous best-in-class, the third-order version. On the screen, you can see the results playing out. Now the y-axis shows the error, so lower is always better. On the left, that's the performance of the older third-order algorithm, and on the right, you can see the new fourth-order one. Just looking at them side by side, you can already tell something is definitely different.
But when we actually overlay them, wow, the conclusion is crystal clear. That red line, representing their new fourth-order algorithm, it just plummets. It finds a more accurate solution in way fewer steps than the old blue line. We're not talking about a small improvement here. It's significantly faster.
And the new algorithm also turned out to be way more robust. In this test, they started messing with a key parameter called friction. And as you can see, their fourth-order algorithm consistently found the best path and just ran circles around the older version, even in different settings. This shows it's not just some one-trick pony. So the takeaway here is incredibly powerful. As we increase P, the order of physics that our algorithm understands, we unlock a fundamentally more efficient way to solve these super complex, high-dimensional problems that are right at the heart of modern AI. And this just leaves us with a fascinating final thought. If we can get such dramatic speed-ups just by teaching AI better physics, what kinds of currently unsolvable problems in science, engineering, and medicine are suddenly going to be within our reach?